You're here because you want to master atomic structure with a University of Cambridge graduate. Let's begin. So for atomic structure, we'll be mainly learning about what is the nucleus of the atom, what does it comprise of, like protons, electrons, and neutrons, and what are they, and also about what is an electronic configuration, ionization energies, and atomic orbitals. Here we also have a list of learning outcomes that I'll be referencing to as we go through the topic together. So for atomic structure itself, we obviously want to know what is the rough structure of an atom. And here we have a very simplified model of the structure of an atom itself. So in the middle you can see in green, this is the nucleus of the atom, and it comprises mainly of protons and neutrons. And around it are these rings that we call shells. And these shells harbor electrons that usually come in pairs. What is holding this whole model together is this thing called EFOA, which is the electrostatic forces of attraction. And we'll be making reference to this EFOA a lot. This is mainly the force of attraction between the nucleus and the electrons, and it's pulling it together. Now, these electrostatic forces of attraction arise because the nucleus is positively charged because it comprises of protons and neutrons, and protons are positively charged or neutrons are neutral. So you have a net positive charge in the center of the whole atom, and then you have these electrons that are quite light, lighter than protons and neutrons, and they have a charge of -1. So as you probably would have guessed, electrostatic forces of attraction are kind of like the magnetic force, or the force between the positive charge and the negative charge. Next up, you would be quite familiar with these symbols already. So you would often see them in the periodic table. So just a quick run through. The top number is called the nucleon number, and this is the mass of the whole atom or the element itself. And here, for example, if you look on the left, chlorine has a nucleon number of 35, which means that it has a relative mass of 35 for the atom itself. And then the bottom number is the proton number, which, as you would have guessed, is the number of protons. And what we can do with these numbers generally is find out the number of neutrons as well that is in this atom. So for example, here, if the proton number is 17, then the number of neutrons would be 35 minus 17. And you would get 18. Right? And also here on the right, you'll see that there's actually another chlorine that has a different nucleon number, but it has the same proton number. And if we calculate, this chlorine has 20 neutrons. But both of these are chlorine, so which is the real one? Well, the chlorine on the right is an isotope of chlorine, and here is a good time to segue into what is an isotope. So isotopes are atoms of the same element with the same number of protons, right, but different number of neutrons. And this is a definition that you should try to memorize. And these isotopes generally have the same chemical properties because they have the same number of electrons, and electrons are what participate in chemical reactions, but they have different physical properties. Now here next is a diagram that you would need to get familiar with. So in general, whenever I try to pass a positively charged or negatively charged atom or ion in this magnetic field itself, or this charge field, there will be a deflection of the atom or the ion or whatever it is. So how you can think of it is, when it is charged, it will go towards the opposite charge direction. For example, here we have an electron, and the electron is negatively charged, so it will go towards the positive charge. And then we also have a proton, and the proton is positively charged, so it will go to the negatively charged. And then here I've also labeled alpha and beta. So alpha and beta are the angles of deflection. And angles of deflection also matter because angles of deflection will be different for different particles. Angles of deflection are dependent on the charge and the mass. So if you have a higher charge, you have a higher angle of deflection, so you would deflect sharply towards the source of the charge. And if your charge is lesser, you'll deflect lesser. Well, this makes sense because you can think of it like a magnetic force, and if your charge is small, your magnetic force is, or your magnetic strength is kind of too small. And then of course the mass matters as well, because if you think about it, let's say you try to use a magnetic strength on a very heavy piece of metal, the piece of metal is not going to move that much. But then when I use the same magnetic strength on a lighter piece of metal, obviously the lighter piece of metal is going to move much faster, given that we have the same amount of magnetic force, right? So that's why you need to take note for angle of deflections and how charged particles go through a charge field. Next up is knowing about what are atomic orbitals. So atomic orbitals generally house electrons, and they come in different shapes and they come in different sizes. So for example, an s orbital kind of looks like a spear, versus a p orbital kind of looks like a dumbbell. And each orbital itself holds a maximum of 2 electrons. Remember what I said in the beginning, how electrons like to come in pairs? Well, there you go. And then we move on to d orbitals. So d orbitals are mainly looking like 2 dumbbells stuck together. How do I remember the naming of the d orbitals is you can go by the axis itself. So for example, dxy over here is the orbital is between the x and the y axis. The same for dyz and dxz. For dx squared minus y squared, the orbital is in line with the x-axis and the y-axis, not between. So that gives this very unique name. And then dz squared is another unique d orbital where it's only along the z-axis. And it's kind of like a dumbbell, but with a little ring around it, like Saturn. And then we need to know that how orbitals are filled generally go along energy levels. So we always start from the lowest energy first and then climb up to higher energy levels. So here I have already arranged the atomic orbitals according to energy levels, and we will start from 1s and then 2s and then so on and so forth, and we'll go up, and only when we have fully filled the orbitals of that energy level, then we can move on to the next one, and to the next one, and to the next one. And here you will note, it's good to take note that there is a slight anomaly, if you can call it an anomaly, is that here you would think that it goes in chronological order from 1 to 2 to 3 and then to 4, but that's not really the case, because here we just need to take note that an empty 4s orbital has lesser energy levels than a 3d orbital. Alright, now we move on to how to determine the electronic configuration. So there are 3 different rules that we have to consider when we fill up the electronic configuration. So firstly is that electrons in the same orbital must have opposite spins. So for example, since electrons come in a pair, they must have opposite spins. So when I draw the electrons in my electron inbox diagram, here you can see that on the left, this is the wrong example, and then on the right, it is the correct example over here, where one is like pointing up and one is pointing down. Then next is orbitals of the subshell must be singly occupied, first with parallel spins before pairing occurs. So if you look at the left, this is a classic example of a wrong 2p orbital that is filled because I'm not filling all of the 3 boxes first, which represent the three orbitals, the 3p orbitals. For example, this is px, py, pz. So I have to first fill Px, then fill Py, then fill Pz singly before pairing them up. And then the last rule is that, as I've already mentioned, you want to put electrons into orbitals starting from the lowest energy and work your way up. When we are removing electrons, it's a bit different from when we are adding electrons, especially for the 4s and the 3d orbital. So remember how I said that an empty 4s orbital over here is lower than an empty 3d orbital? Well, when the 4s orbital is filled with electrons, the 4s orbital is actually higher in energy level. And as it turns out, when I'm trying to remove electrons, I also want to remove in the chronological order from the highest to the lowest. So I will remove electrons from the 4s orbital first and then the 3d orbital. On to some more anomalous examples. So there are two main examples that do not really follow the above rules. So one of them is chromium and then the other one is copper. And as you can see that whenever the 3D subshell hits a 5 and it can hit a 5, then the electronic configuration would favor it such that the 3D one will hit the 5 and then not fail the 4S one doubly first. And this is because that copper and chromium, with these half-filled or fully filled subshells in the 3D orbitals, this tends to be more stable due to symmetrical charge distribution. So if I were to draw it out, if I were to draw out the 3D orbital here, right, I would split this into 5. And then here, it's also split into 5. And what they're trying to say is, for chromium, I want to singly fill everything here versus the one on the right, where I only fill 4 of it up and fill up the 4s orbital fully. So this right one over here follows the energy levels, right? Because I want to fill my 4s first, then the 3d orbital. But then it was just found that it's energetically favorable to the left than the right. So we will go for the left over than the right. And the same can be said for copper, except that we're talking about fully filled d orbitals, right? And the main reason is because that if you have only one electron in the 4s orbital, you will have reduced inter-electron repulsion. Alright, and now we move on to another foreign term, that is ionization energy. So ionization energy is defined as the energy required to remove 1 mole of electrons from 1 mole of gaseous atoms to form 1 mole of singly positive charged gaseous atoms. Please memorize these definitions, it's very important. Exams love to test this. Some facts is that it's generally a positive value because I'm removing electrons, so I'm overcoming the interaction. And here, this is mainly talking about the EFOA. So since I'm trying to overcome it, I have to input energy into it. So this tends to be endothermic. And if you don't know what endothermic means, it just means that it's energy is input into the system itself. And in general, the second ionization energy is greater than the first ionization energy, because after removing an electron from an atom, it becomes positively charged. And when you try to remove an electron from a positively charged ion, it's harder because a positively charged ion is positive charge and electrons are negative charge. There's going to be a stronger force on the second electron and moving forward as well. So some of the factors that affect ionization energy is the resistance of the outermost electron from the nucleus, shielding effect, and nuclear charge. And I'll explain how you can use each of them when explaining what the comparison of ionization energy is between different atoms or different elements and other means of comparison. So if we're looking at the trend down the group, you'll see that down the group, there is an increase in nuclear charge because nuclear charge is determined by number of protons. However, the number of electron shells down the group also increase, right? So because of that, your valence electron is further away from the nucleus. And if you can imagine this, if it's further away, the distance is greater. And because of that, the electrostatic forces of attraction is weaker. And therefore, if the electrostatic forces of attraction are like the magnetic force, it's weaker, so the electrons on the outermost have an easier time of being let go. So the ionization energy is lower. And now about the trend across the period. Well, the trend across the period suggests that the number of principal quantum shells is the same. So there's not really an increase in shielding effect in general, right? But then the nuclear charge increases as well because the number of protons increase. So when you compare these two, you always want to take nuclear charge and shielding effect into consideration, right? And because overall there's an increase in nuclear charge, so the effective nuclear charge increases. Effective nuclear charge increase means increase in EFOA between the nucleus and the outermost electrons, and therefore increase in EFOA means that your ionization energy will increase because the magnetic strength is higher. So if there's more force pulling on the electron, you need more energy and more force to pull it out. So there's an increase in first ionization energy. All right, and of course with every rule there's some anomalies. So for example, when we're going from group 2 to group 13, when we're trying to go across a period, right? So here's an example. Group 2 we have beryllium, and then group 13 we have boron. And you can see that in boron itself, right, because I'm trying to remove an electron from the 2p orbital, it's at a high energy level than the 2s electron removed from beryllium. So this one. So this is the electron that I'm trying to remove from both of them. Because the 2p electron is at a high energy level, it actually takes lesser energy to remove it. So if you look at the trend, there's a dip from beryllium to boron itself for first ionization energy, only looking at the first. And then you can also see that there's a dip between nitrogen and oxygen. So from group 15 to 16, right, there's also a dip because when I go from group 15 to 16, you can see that 16, right, is a 2p4 versus 15 is a 2p3. And this matters because if you look at the diagram over here, it's easier to remove an electron when it's paired versus when it's not paired. So for example, in 2p4, the electron I'm removing is paired, right? And this is because of interelectronic repulsion. In general, electrons don't really like to stick together because they're both negatively charged. So it tends to be easier to remove something that's paired, and because it makes it more stable. So it requires lesser energy to do that. Therefore, the first ionization energy of oxygen is lower than nitrogen. So just take note of these two anomalies because they are more likely to be asked in the exam. And take note of the explanation. It's pretty straightforward. Right? Now on to successive ionization energies. So whenever you're given a graph of successive ionization energy, I think it's just important to take note of general trends. So when you see successive ionization energies, aka when electrons are being plucked left, right, and center from the same atom, and they keep plucking and plucking electrons, right? Right? In general, there is an increase, right, as I keep plucking electrons. So you can see as we go towards the right over here, right, the energy increases upwards. And this is because of what I mentioned just now, that when I pluck out an electron from an atom, it becomes a positively charged ion, and it becomes harder and harder to yank electrons from this positive ion, right? So that's trend number one. And then trend number two is that you can see very significant jumps in the ionization energy from different electrons being removed. So for example, over here and over here. And each jump, each very significant jump, is implying that there's a removal of an electron from the next shell, The biggest jumps in energy for ionization energy is when I'm trying to remove an electron from an outermost shell, and then suddenly I have to remove something from an innermost shell. So just take note that as for successive ionization energies, that whenever there's a decrease in interelectronic repulsion, there's a decrease in shielding effect as electrons are removed. And since my nuclear charge remains the same because I'm removing it from the same atom or an ion afterwards, right? The effective nuclear charge increases and the EFOA will just increase, and the next IE is always higher, right? And every large increase in IE observed equals to a change in the principal quantum shell. It means that the next electron I'm removing is actually from the next shell, the next inner shell. Atomic radii also has a similar trend to ionization energy, where if you can see that it uses the same explanation, right? As we go down the group, the nuclear charge increases, but my number of shell increases, and because of that, the valence electrons further away. And as you can expect, if I have more shells, right, it means that the atomic radii will increase. And the atomic radii is the distance between the nucleus and the outermost electron. So because of that, you also have weaker EFOA between the nucleus and the valence electron. So the strength of your EFOA will decrease, and that means your atomic radii will increase. So you can see there are parallels between ionization energy and atomic radii. Okay, how about across the period? It's also using the same explanation where the number of principal quantum shells are roughly the same. So the increase in shielding effect is negligible. And then we look at the next factor, which is nuclear charge. Nuclear charge increase because number of protons increase, and therefore effective nuclear charge increases, and therefore my EFOA strength increases, and because of that, it's like pulling the electrons closer to the nucleus, so the atomic radii is gonna decrease. So that's it for atomic structure. Hope to see you in the next lesson.